It's a great honor to be here. I've known a number of the members of the Georgia Tech Chemistry Department for quite some time. In fact, I've known Joe longer than I've known Seth. We overlapped in graduate school, and all of the best Halloween parties were at Joe's house. And so we were quite sad when he moved on to JPL, and we had to find other places for Halloween parties. But again, I want to thank everybody that I've met with and spent time with over the last couple of days. It's been a really enjoyable couple of days, and I feel bad that it took me this long to get to Georgia Tech, and it certainly won't take me another 53 years to come back again. But so what I'm going to tell you about today is some of the work that we're doing in organic solar cells, and as you'll see from the approach we're taking here, that in some ways it mirrors the kind of chemistries that we developed in organic LEDs. And as Jean-Luc said, we spent a lot of time developing materials, but a lot of that was really geared around trying to understand what the problems were. And so a lot of it was geared around figuring out what the limitations were and trying to figure out how to get around those. And so let me start today with a short outline of what I want to cover. And so I've got two pictures here that give you a picture of where we would like to be and where we are. The picture on the left is the roof of the Air and Space Museum in Washington. It's covered with single crystalline silicon solar cells. The picture on the right is a panel produced by Konarka, and that's a bus stop in San Francisco. So that's an organic solar cell, and this is an inorganic solar cell in the language that I use. And so the inorganic solar cells, silicon and others, are quite high efficiencies. You can actually buy a single crystalline solar cell now whose module efficiency is within a few percentage points of the theoretical maximum efficiencies. Organics were not quite so good. The record efficiencies now are somewhere between 8 and 9%. And so in terms of the next hour or so, what I want to talk about is, first of all, to give you some background. I'm going to assume that there's enough people in the audience that don't work with solar cells and organic photovoltaics that a little bit of background and some description of how we do the measurements is beneficial. I'm going to then talk about the chemistries we're doing trying to push our absorption energies out into the near infrared, talking specifically about two different donor materials, Squaraine donors, and some work we're doing with Porphyrins. And then I'm going to talk about some work that we initially started out with an idea. We were looking at panchromatic absorbers, where, remember, we have to absorb the whole solar spectrum, right? That we unfortunately we're limited by the sun, and developing solar cells for some other star is really not useful. And so we have to live with the solar spectrum, which is a broad dispersed source. And so our original goals were to make panchromatic absorbers, but we think we found our way into some much more interesting science sort of in trying to solve that problem. So let's think about where we are. And this is a slide that many of you have already seen. In fact, this one is about 6 months old, which means there's a dozen data points missing. NREL is the National Renewable Energy Lab. It's a national lab whose key focus is on developing renewable energy. NREL is the source of the efficiency measurements that we make. They are the ones who validate solar cells. So if you want to claim you've got a world's record, no one's going to believe you, and they won't let you publish it until NREL certifies that value. So the data in this plot doesn't represent really the whole field. What it represents is data that they collected internally at NREL. So you can see starting in about 1975 is when they started certifying cells. And if you look, all these different color lines have to do with different solar cells. And so if you take single crystalline solar cells, which are up here in those squares, you can see the efficiencies are pretty good. They're getting upwards of the high 20s, 27, 28%. Turns out you can buy a single crystal silicon solar cell now that is about 26% efficiency, which is pretty good, considering the world's records are on the order of 27, 28. The cells in purple are tandem cells. So those are two cells stacked one on top of the other. You get quite high efficiencies, and people debate whether they can afford them to put them on satellites, let alone the roof of your house. They're actually quite expensive. So when you think about terrestrial solar, you stay in the single junction cells, which are the blue, green, and red part of the curve. So then you look at organics and say, geez, we're not doing so hot. But keep in mind, the first organic solar cell that had an efficiency in excess of 1% was only reported in 1986. And that if you look at the progress in the last 4 or 5 years, it's actually been quite good. Now, if you look at a plot like this, and again, if don't work in solar, you might look at this and say, well, this is good, but 25%, that doesn't sound so hot. 30% doesn't sound so high. Turns out that if you actually go back and evaluate this, and I want to explain why, some of these numbers are pretty close to the theoretical maxima. And so if you think about the solar spectrum, this is it. This is what we get at the surface of the Earth. All those notches are cut by the atmosphere. So it's a black body source. This is what we actually receive, and you can see it's peaked somewhere 544 nanometers or so is where the peak of the solar spectrum is. And so if you think about this, and let's think about this in the context of, say, silicon, the most common material to make solar cells out of. The energy gap is about 1.1 electron volts, which I've indicated here by an arrow. And so that means that silicon will absorb all the photons whose wavelength is, or whose energy is above 1.1 and nothing below. So we can first of all strike out that part of the spectrum. Right? Anything whose energy is below 1.1 AVs is not going to be absorbed. Then you run into another problem, an even bigger problem, and that is that silicon is a semiconductor, and I can excite from anywhere in the valence band to anywhere in the conduction band. And that's fine, and that's good. It gives me a nice broad absorption band, but the problem is that all of those different photons have different energies. And so when I think of the total solar energy, right, I've got very high energy at low wavelength, and the energy gradually drops off. The blue line shows you the energy per photon in electron volts. So if I absorb a blue photon, what happens in silicon is within a matter of a picosecond or so, the energy that I deposited into the silicon with the blue photon is all dispersed as heat, and I now have an energy gap exciton. So I've got something at sort of the purple line I show here. And so all those high energy photons all thermally relax to the lowest energy state. And so if I correct the spectrum, so if I take my AM 1.5 spectrum and correct it for this energy drop, I get the green part of the curve. So that's all I collect, is that green part of the curve. So that's the best I can do if I recalibrate this for the energy I can get. And you say, well, that looks okay. Well, and you're not going to get all of that, right? It's sort of a problem of the second law of thermodynamics. You don't get everything you think you can get. Turns out when you go through and do a thorough thermodynamic treatment of this, the best you can do in any single junction solar cell is about 31%. The best you can do for silicon is about 29%. So when I showed you those numbers, and we looked at the curves, and we had silicon solar cells that were putting out 27 and 28%, we're within 1 percentage point of the theoretical maximum. So when we were doing our work with OLEDs and getting into the 80s, 90s, even 95% range for efficiencies, that's the equivalent of 31% here, or 29% for silicon. There's a recent paper that just came out of, this is Giebink, Forrest, and Wasilewski, went through and did a thermodynamic analysis very close to the one that Shockley and Cuisier did in the 60s for organic solar cells, and they expect the maximum for an OPV is somewhere in the neighborhood of 25%. Depends on the order of the system and how much entropy plays into this, but it's expected that we should be able to get into that range if we get all the materials right and optimize the cells well. So there's some hope, right? So if we think about our organic cells being here at 7.9%, if we get everything right, we can get up into the range where we see for things like silicon and better than cad telluride and others. So now let's talk about what we want to get to. This is the kind of data you're going to see plots like this periodically through my talk. These are IV characteristics. The dashed line is the IV characteristic that we measure in the dark, and the solid line is what we measure in the light. Right? And so the device structure is shown here. It's a pretty simple device. There's a donor layer and an acceptor layer. The difference between the dark curve and the light curve is the photocurrent. Right? And so JSC, or the short circuit current, is what you see at 0 applied bias. As you go to higher and higher bias, what we're doing is applying a voltage that opposes the voltage that we're making in the photochemical cell. So we're applying in the forward bias regime. Ultimately, we apply enough voltage to the device that we shut it off. And so at VOC, which is the open circuit voltage, that's when we've shut the device off. And so those are two important parameters. But the parameter that people worry the most about is the efficiency of the cell. The efficiency of the cell, which is A to P, is simply the ratio of the maximum power to the incident power. So it doesn't matter what was absorbed, it's just how much power do you get out versus the power you put in. And the power out is easy enough to get. If I take the product of the current and the voltage, I get the purple curve I show here, and that's the maximum power. If I go to the peak of that, that's the maximum power I can get out of the cell. So that current and voltage combination that I call VM-JM, that product is P max. And so when you see the data, though, nobody talks about Pmax, and they don't talk about Vm and Jm. We talk about JSC, VOC, and this thing called the fill factor. Well, the fill factor actually is directly related to Pmax. You'll oftentimes see it drawn this way, where you see these two rectangles. The fill factor is simply the ratio of the maximum power rectangle, which is JM-VM, divided by the product of the short circuit current and the open circuit voltage. So it's an arithmetic way of pulling out more factors, because I'll tell you, when you're thinking about devices, it's very helpful to be able to think about them in terms of subsets of problems. And if all I really had was the ability to optimize efficiency, I'd be stuck. But this way I can think about this as terms of three terms: the short circuit current, the open circuit voltage, and the fill factor. And in many ways, they act independent of each other. So it's a real benefit being able to separate this into three, not independent, but I'll pretend they're independent parameters. Right? They're actually somewhat interrelated, but you can still think about them simultaneously as independent parameters. So how does a solar cell work? So it's a little different than a silicon solar cell or a gallium arsenide or a cad telluride. In organic materials, the exciton has a relatively high binding energy, somewhere between 300 and maybe even upwards of 1 volt binding energy for that exciton. What that means is, in contrast to semiconductors, inorganic semiconductors, where the exciton itself is not bound, at room temperature it spontaneously makes the hole in the electron, we have to go to an interface. And so if we start off here, we absorb a photon, we make an excited state or an exciton, the exciton diffuses to the interface between the donor material and the acceptor material. That at this point, the driving force for creating the charge, creating the hole in the electron, is electron transfer from what I'm showing here as the excited donor to the acceptor. So once I've generated those two charges, they diffuse to the electrodes, and there's my photocurrent. And so you can think of it in these 5 steps, and it is pretty much in these 5 steps that the process occurs, but those actually lead to some serious limitations. Right? The first one is that the spectral overlap is actually a big problem. So if we just start with this first one, that is the light intensity, the light impacting on the organic materials. Remember I said silicon has a gap of about 1.1 electron volts, so it absorbs everything out higher in energy than 1.1. Well, let's think about what that means and where organics get to. So this shows you that same spectrum I showed you a minute ago. This is Watts incident versus wavelength. And I've indicated where the visible part of the spectrum is, so you can just get a feeling for that. And this doesn't tell the whole story, because remember, the vertical axis is in watts. So if I change it instead and show you what and change the vertical axis to flux, so now I've divided by the energy of the photon, this is how many photons are impinging on that same area per unit time. And you can see that there's a lot of photons out here in the near infrared. The problem is that they're underemphasized in that other plot, simply because I've shifted everything in terms of watts. So how well do organics do? Well, most of the organic solar cells that you're going to find out there are absorbing at around 800 nanometers and lower. Right? They don't go much beyond about 800 nanometers. Silicon goes out to about 1100 nanometers, 1.1 eV, and so that whole gray area is not being used. So you can imagine if I look at my solar cells, and remember everything relaxes down to this energy, so this integrated area is what I'm not collecting in my organic solar cells. And so there's a huge loss. That's a huge limitation. And so there's a lot of people, my lab and elsewhere, that are pushing the absorption manifold as far out as we can, because that gray area is what we want to collect. There's another problem that comes from this as well, and that is that because the exciton is so strongly bound, it doesn't migrate very well. That is, there's a relatively big reorganization energy for the migration of that exciton. And so typical exciton migration lengths are on the order of between 10 and 30 nanometers. And so what it means is that if I think about this diffusion process, step number 2, if my organic layer is thicker than, say, 30 nanometers, it doesn't matter how thick I make it after that, because none of the light absorption will lead to excitons that get to the interface. Remember, only excitons reaching the interface are useful. The rest of them are wasted. And so it limits the amount of material so that you can't make your devices very thick, at least in that lamellar structure I showed you before. Now, fortunately, there's a solution for this, and it's called the bulk heterojunction. If instead of using a lamellar structure, where I've got a single layer of donor and a single layer of acceptor, if I use something like this, that is a sort of bicontinuous network, now the exciton doesn't have to diffuse through a thick layer, it only needs to diffuse through this fingrel. And so long as this distance is on the order of the exciton diffusion length, you can do pretty well. And so now, in a bulk heterojunction device, you can actually get quite high short circuit currents because now your light collection is not limited by the exciton diffusion length. And so the most efficient cells, the 8% cell, there's a 9% cell, there's one that's supposedly higher than that, but I'm not certain if it's a bulk heterojunction, but the higher efficiency cells are all this bulk heterojunction. And it's really designed around solving the short circuit problem, the short circuit current problem. The other problems that come up are the carrier conductivity must be high. This is something organics are terrible at, and that impacts the fill factor, so that how steep or how much like a hockey stick the curve looks like has to do with the conductivity. And we typically solve this by keeping the films thin, but remember, if I keep the films thin, I don't get much light collection, so that's a bit of a problem. And the open circuit voltages are typically low, and I'll talk a little bit about that in my talk, but most of what I want to talk about is going to relate to these first two. In fact, I'm only going to talk about the second bullet for one slide, and then the rest of it's going to be about the first bullet, which has to do with light collection, doing a better job of spectral absorption. So let me start here, because this is my one slide on exciton diffusion, so that I can admit that I failed and we can move on with it. But we started with this compound where remember, our initial issue was light absorption. That I want to collect a lot of light. So that means I want things that have big extinction coefficients. And so at the outset we said, what has a big extinction? Well, porphyrins have great extinction coefficients. Nature learned this 2 billion years ago. So a lot of light absorption is in chlorophylls and porphyrins and other related macrocycles. So we had this platinum tetrabenzoporphyrin molecule floating around the lab. We'd actually used it to make near-infrared emitting LEDs, which were actually quite good LEDs. And this was a case where two students with adjacent desks actually talked to each other, which was a good thing. So Karsten handed Dolores the sample, and Dolores went and made the devices. And so you can see here, these are thin films. The black trace is copper phthalocyanin, the red trace is the palladium compound, and the blue trace is the platinum compound. And when she first made this, she thought, this is great, right? This has a long lifetime. The measured lifetime was 55 microseconds. And so if you look at the simple models for exciton diffusion, where LD is the exciton diffusion length, it's equal to the root of the diffusion coefficient times the lifetime. So if the lifetime is really long, the exciton diffusion length should be really long. And so, and we know the lifetime is going to be long. It's a measured 50-second lifetime. I'll talk about this later, but we know the intersystem crossing rate is quite fast. So the question is, does it give a long diffusion length? No, it doesn't at all. It's quite short, actually. It's about 6 nanometers. This has to do with trapping, and it's a whole nother part of a seminar I don't want to get into, but the interesting thing is where this led us in terms of the chemistries that we did to develop better chromophores for longer wave absorbers for platinum and other compounds. So first of all, let me go back, but we did make devices with this. And so the first question that comes to mind is it's a triplet. And in organic LEDs, we were happy with triplets because their energy is low and they don't get lost. They have long lifetimes, and you don't get a lot of quenching due to energy transfer to alternate sites because the energy of the triplet is so low. So the question is, what if the energy of the triplet is so low that this exciton no longer has enough energy to be able to charge separate at the donor-acceptor interface? And so if we look at these, we can actually estimate that. So we can estimate what the oxidation potential for the excited state is for both the singlet and the triplet. And so this is the triplet's oxidation potential and the singlet's oxidation potential. This is the reduction potential for C60, and you can see it's just fine. That both the singlet and the triplet are fully competent to charge separate. And so if it had failed this test, and I showed you the next data where we actually get a nice IV characteristic, you would have wondered about the test, but it works fine. So it explains, sure enough, we get an IV characteristic that we expect. So the red trace is the platinum porphyrin, the black trace is copper phthalocyanin. And this looks good. We get a nice efficiency, we get a big efficiency bump going to the platinum porphyrin, and that was a benefit. But the thing that was a serious surprise was this open circuit voltage. This was not what Dolores expected. She expected exactly the opposite. She expected the platinum porphyrin to have a lower potential than the copper compound. The reason is if you look at the energetics of these, and let me get rid of the dot, if you look at the energetics of these, the energy of the whole, which is given by, approximated by the HOMO energy, is less for the platinum porphyrin than for copper PC. The energy of the electron is fixed by the reduction, the LUMO level of C60, And so this energy difference between the hole and the electron should be related to the open circuit voltage, and it doesn't appear to be. In fact, it's inversely correlated. A small interface energy difference gave rise to a fairly large open circuit voltage. And so it's worth thinking for a minute about where the open circuit voltage comes from, because it took Dolores a year and a half to get from this point to where she handed me her thesis, because she had to answer this question before she graduated. So I'll do this in 2 slides. But the key is, where does the open circuit voltage come from, right? And in the same way that we teach you in freshman chemistry that an equilibrium is not a static situation, but a dynamic situation where you have 2 reactions whose rates are balanced, the same is true here, right? The open circuit voltage is when the current produced by the light reaction, which is charge separation from the excited donor, is exactly balanced by the current injected at the contacts. So you can think of, this is my light reaction. This is what happens if I turn the device off and I run the bias in the backward direction so that the current exactly compensates or wipes out the current that's there. And so it's the balancing of those 2 rates. And when the rate of current production equals the rate of current annihilation, we're at the open circuit. So the question then is, the maximum open circuit voltage I can get is given by this energy difference, but we never get that. So what limits how close we get? And I'm showing you here 2 different imaginary curves. The one in black, you can't easily tell black versus red, but this one here is a high dark current, and this is a comparatively low dark current. And so remember, and the photocurrent is the same for both of these. So the point where the open circuit voltage occurs is when the photocurrent exactly equals the dark current, which you can see for the high dark current happens at a much lower voltage than the low dark current does. So anything I can do to slow down this back reaction, anything that slows down this dark reaction, or the reaction that would occur in the dark, anything I can do to slow that down will increase my open circuit voltage, because it will decrease my dark current. So if I go back and look at the molecules, the ChemDraw pictures don't tell you the story at all, because this suggests that the structures of these 2 are quite similar, and they're not similar at all. This is a side view of the copper phthalocyanin, and this is a side view of the tetrabenzoporphyrin. The phenyl groups in this case are flanking it, and in fact the porphyrin molecule itself looks like a Pringles potato chip. It's not at all flat. It's very heavily distorted. And if we make close pack models, and this is not the kind of calculation that would be done in the Breda group, this is a PowerPoint calculation where I simply cut and pasted from two different calculations. And most of my time was spent figuring out how to get rid of the white box that surrounded the C60. I spent at least an hour figuring out how to do that, so that was more time than the total calculation time. But the point is that the phenyl groups that are here, you can see space the hole and the electron quite a bit further apart than the hole and the electron in CuPC C60. And so that spacing, by doing this, I don't stop the back electron transfer, but I slow it down. You can think of this in the simple Marcus electron transfer argument. The further apart the hole and the electron are, the slower the rate of electron transfer between them. And I don't want to go into, this is another half an hour worth of talk, but we've looked through and modeled this in a number of systems and see the same behavior. That anything we can do to increase the distance at the donor-acceptor interface will increase the open circuit voltage. And will get us to start approaching the upper limit that we see here. That is to say that we can start getting closer to what the maximum efficiency is if we can push the start current further out. So there we are, and then we look at these numbers and say, this is good, but if this was such a great device, why are we only getting 1.9%? Well, we're back to our light absorption problem. The blue curve is what I need to absorb, and the red curve is what I do absorb. The lines are way too narrow. It's one of the problems with tetrabenzoporphyrin and things like it, is that they have a high extinction, but their lines are quite narrow, so it doesn't do me any good. So the next challenge was, how do we get high extinction and broad lines? And so the next high extinction molecule is one that's well known to a lot of people in this department. I know Seth's group has done a lot of work with Squaraines looking at the NLO properties of them, really tied to the same things we're looking at here, very high extinction, very high polarizability, and so on. If you look at these show you, these are the stolen out of this paper, but you can see these all have extinctions between 10 to the 5th and 10 to the 6th, which is really good. These are small molecules with very, very high extinction coefficients. And if you look, this is one of the compounds I'm going to spend most of the time talking about. The red curve is the solution spectrum, and the blue curve is the thin film spectrum. So I get a very high extinction, And I also get a very broad line with a high optical density for the thin films. So this has a peak optical density of 4 × 10⁵ per centimeter, which is really high, and a line width of what, almost 200 nanometers. So it's quite a broad, exactly what we want. We weren't the first people to make devices. We actually got scooped by the Tobin Marx's group at Northwestern. They made some devices with this particular derivative where they were pushing to try to get out into the near infrared. These are bulk heterojunction devices. Oh, and I lost the legend. These are 4 different devices. This blue trace is the one I listed here. It's the best device that they had, which has an efficiency of about 1.2%. But the key is these were bulk heterojunctions made by putting down a homogeneous film and annealing them. So they don't know anything about the spacing in these. And so we wanted to go back and make lamellar devices where we could carefully control the thickness and potentially learn something about these as a class of donors. What's the diffusion length look like? How good are they at transporting holes, and so on. And so the first set of devices that we made are shown here, and this was one where CE and I were quite surprised. In fact, she wouldn't show me the data. This happens all the time, where a student will find something that's exceptional, and they'll make the device 2 or 3 times before they'll tell me that they made it, because they don't believe the data. They want to make sure that they didn't screw up and make the wrong device. So she made 3 or 4 of these before I saw it. Turns out, if you take 65 angstroms of that squarane, this one, the diisopropyl squarane that I show here, and the reason we chose this one is it's the only one on that list that we found that actually can sublime. This decomposes when it sublimes, but you get about a 35% yield, and the decomposition product never leaves the boat. So it never goes into the devices, which is good news. But she gets an efficiency of about 3.2%. You can see here's this is the efficiency, the quantum efficiency is a function of wavelength, and you can see her photovoltaic quantum efficiency matches the absorption spectrum pretty well. She gets about 3.2% for 65 angstroms of material. So we're converting over 20% of the incident solar light into electricity with only 65 angstroms of the squarane. Sort of gives you an idea of how big this extinction coefficient is. So I said, geez, if 65 angstroms is good, then more is better, and it turns out it's not. It turns out the exciton diffusion length here is about 60 angstroms. We've measured this by luminescence measurements. And so you can see as she makes the film thicker, there's not a real gain. In fact, the current starts dropping. So that's 65 angstroms. Let me go down. This is 110 angstroms, 150, 200. The current is dropping because as she puts more and more squarane in, we're radiating from the bottom, and it's actually attenuating the light before it gets into that last region between C60 interface and the absorption window. So we can't make it much thicker than this, although I'll show you in a minute we can actually. If we play the games right, we can get a little bit thicker and do better than the 3.2% that I'm showing you here. But there is a problem with resistivity. Right? This is an amorphous film. If you notice, the fill factor is dropping. We go from 0.6 down to 0.5, and that's because as we make the film thicker, series resistance goes up and the fill factor drops off. So if this is an amorphous film, crystalline films have better conductivity, both carrier conductivity and exciton conductivity and mobility. So what happens if we anneal it? Well, the powder spectrum is shown here, and I just realized this morning that's not indexed correctly. This is an older slide. That's indexed correctly. This is indexed wrong. But the key is we have the single crystal structure that I'll show you in a few minutes. But if we start with the film, you can see that there's the trace here. There's no annealing, and there's nothing to see. We go to 70 degrees, there's nothing. 90 degrees, there's nothing. When we get to 110, we start seeing a peak grow in. If we go to 130, it gets even bigger. It's a little bit clearer here. If we anneal with methylene chloride, it gets huge. And so the question is, we're getting crystallinity built into these films. And so I'll show you what the structure of this is in just a few minutes. But the question is, does that crystallinity help? Right? It should, but does it help? First thing is, when we tried to make films with the dichloromethane annealed ones, we got terrible devices. And that's because this is the DCM one. By the time you crystallize this much, there's huge areas of open ITO underneath. And so when I vapor deposit the acceptor on, I get direct shorts between the acceptor and the anode, and that's bad. So if we anneal it at 110 degrees, we do quite a bit better than that. In fact, you can see here that now we go from about 3.2%, 3.5% or so for the unannealed materials up to almost 4.5% for the annealed devices. We do quite a bit better than that. And so then the next question was, so annealing helped. So how do we stimulate sort of intermolecule interactions? So we thought, well, what if we build in pi systems? What if we build in aromatic groups like these? So if we, instead of making the diisopropyl derivative, we make the diphenyl derivative or the naphthophenyl derivative. Now, those don't sublime. So the data I'm going to show you in a few minutes is all for solution process devices. But the key is that if we look at the structures of these, this is the isopropyl derivative, this is the diphenyl derivative. We haven't been able to get crystals of this one yet. But if we look at the packing diagrams for these, they're really quite different. For the isopropyl derivative, it forms a pretty standard sort of herringbone packing. Nothing special. The intermolecule spacings are pretty long. There's not a lot of intermolecular contact. When we go to the diphenyl derivative, it actually forms a slip stack of dimers, where the spacing here is about 3.5 angstroms or so, where the packing is not between the phenylene end groups, but it's actually the closest spacings are between those cores, between the squarane cores. So it looks like we might be a little bit better off if we can induce this sort of crystal form in the films, that we might be better off in terms of both exciton transport and carrier transport. Another big benefit from these is if we look, these are the solution spectra now for my parent squarane, which is the isobutyl derivative. The diphenyl is in blue and the phenylnaphthyl is in red. Remember I said I wanted broad lines? Look at those. We're double the width, and this is in solution. So remember, my normal squarane, when I went from this derivative into the thin film, it more than doubled in line width. So if these more than double in line width, I'm going to be way out here somewhere. And that was what we were hoping, not what we observed. This shows you the black trace and the thin black line is solution in thin film for the isobutyl, and the blue trace and the thick blue trace are for the phenyl. Turns out in the thin films, the line width is the same for all of them. Doesn't make any difference whether it's the diphenyl, the phenylnaphthyl, the pyrene phenyl. We've made a dozen of these, and they all have the same sort of line width. On the order, still quite broad though, 3,100 wave numbers or so with line widths. Nice extinction the way we're looking for them. So if we put these into cells, we do pretty well, right? So this is, we get about 3.2%. Remember, these are solution processed. So a reference device here, this 1.8% that we're getting here, remember when I did a vacuum deposited device that doesn't have solvent and I don't have any problems of handling in air and so on, was about 3.2%. So we're doing pretty well, but let's see if we could do better than that. What if we thermally anneal these? Because remember, I bought myself almost 70% improvement in efficiency when I annealed them. So now if we anneal this one, so we start with a film of the naphthophenyl. So we start with this material, this one. The one alpha naphthophenyl squarane derivative. And I start annealing it, and they're only showing 3 temperatures here. We looked at a wide range of them, 80, 90, and 110 degrees. And you can see that, the dashed lines don't show up so great. But at 90 degrees is where we get the biggest EQE. That is to say, we get the biggest enhancement of the efficiency that we see. We get fill factors that are on the order of 64% compared to, well, that's 64 also, compared to 53 for the squarane, the parent squarane. So we have better carrier conductivity, better exciton mobility. This is now 200 angstroms thick. We're getting 10 milliamps per centimeter squared, 5.7% AM 1.5. And keep in mind, this is 5.7%, and I'm not collecting very many photons between 500 and about 650 nanometers or so. This is the peak of the solar spectrum, not a valley in the solar spectrum. And so as we're now filling, which you'll see I have some strategies for filling that I'll talk about in a few minutes, we should be able to push this up much higher than where we are now. So we're quite enthusiastic when we saw 5.7%. We've actually made hero cells that I'm not going to show you the data for because they're hero cells that are about 6.5% with the same material. But unless I could tell you how to do that in your lab, I don't like to show you the data. And I don't know how to do it in my lab, so I couldn't tell you how to do it in your lab. But you'll occasionally get even higher numbers. So this is, oh, and one more thing to point out is that the structure that we're doing here is something that we don't think of as a bulk heterojunction. So we're annealing the film in the same way you anneal a bulk heterojunction, but it's not a bulk heterojunction in that we're not making interpenetrating networks in the same way that you do in a P3HT PCBM bulk heterojunction. What we're doing is we're heating and crystallizing, so we're forming a nanocrystalline layer of donor and then vapor depositing the acceptor on top. So this actually gets toward the ideal structure for a bulk heterojunction, which are sort of dendrites and stalactites and stalagmites that are interpenetrating into each other. And this phase is continuous and directly connected to the anode, and this phase is continuous and directly connected to the cathode. So if we can get even a little bit more conduction, if we could get up to 300 angstroms in this layer, we'll do tremendously better. Because we're already sitting at about 25% as it is. So if we get another 100 angstroms or so, which we think is very doable, we should be able to push up into the 8 or 9% range for a single junction cell like this. Now what about porphyrins? Remember I said I started out on porphyrins because they had such high extinction. And we actually showed that we could put, if we go from the platinum OEP, which is shown here in blue, if I benzannulate it, I can go redshift significantly. And this tetrabenzo is the one I showed you a minute ago. If I make the naphtho derivative, I can redshift even further and get out to absorption that is close to 700 nanometers, but they're all narrow, right? And that's a big problem. So we wanted to broaden the lines, and so the question is, how do we do that? There's two different approaches. The one I'm going to talk about today is sort of extending the pi conjugation in the meso position, and we got this lead from some work we were doing in detectors. So DARPA came to us, or I guess we went to DARPA, but I like to think that they came to us, and said that they wanted photodetectors that worked in the near infrared. And they ideally wanted organic photodetectors that worked out to almost 2 microns. And that was, we've never gotten to 2 microns. But the question was, how do we get further into the near infrared in a photodetector? So our challenge was to find things that I could convince my electrical engineering colleagues to actually put in a device. So they needed an absorption of greater than 10 to the 5th in the near infrared. And I said, I don't know how to do that. That's terrible. I don't know how to do that. And so we started hitting the literature, and we discovered that if we go to these porphyrin tapes, this porphyrin dimer tape, this triply bridged tape, looks like this, and it's pretty good. Its extinction is 5 times 10 to the 4th, out to about 1100 nanometers, and that we can string 3 porphyrins together, 4 porphyrins together, 5 porphyrins together, and as you would guess, they get progressively less and less soluble and more intractable. And so what Slava did is said, look, I have another idea. So what if I take pyrenes that he put on here to sort of cap the ends of this so that it wouldn't just run away and oligomerize? What if I treat that with iron using what's called Scholl conditions? I can fuse that and make this doubly fused pyrene compound. And so now we get a marked redshift and an increase in intensity by quite a lot. So the intensity goes up by about 30%. I get a redshift out beyond 1200 nanometers. The tail is out to 14. We've actually, using this same system, gotten to absorption out to about 1800 nanometers. But the key is, this is all great, but remember, I don't care about any of these photons. Right? If I were to make a solar cell with this one that's absorbing out to 1200, my open circuit voltage might be 50 millivolts or something. I'm going to thermalize all the way down to here. The highest efficiency solar cell I'm going to get in a single junction cell needs to have an edge that's right here at about 950 nanometers. So even the dimer is already too red to use in an efficient single junction solar cell. So what I really want to do is fuse this one. That is the monoporphyrin. So we throw it in iron trichloride, no reaction. We tried scandium triflate, we tried TDQ, we tried every set of conditions we could find, no reaction. So we got frustrated and just heated it up, and fortunately it works. If we just heat it to 500 degrees, it goes just fine. Quantitative yield of the fused compound. If you take the dipyrene compound and heat it, this was done sort of by accident and sort of intentionally. When he goes to sublime it, this will sublime cleanly, but what's left behind in the boat is this. It partially decomposes even under vacuum. If you put it under an atmosphere of nitrogen, you get quantitative conversion to this mixture of isomers, the syn and antiderivatives. And now these have the benefit that because of the steric interactions here between what I call H-alpha and H-beta, these are not planar compounds. These are actually quite soluble. You can get many milligrams into a milliliter of THF. It's actually really soluble compounds for porphyrins. They come out in this 1-to-1 ratio. This shows you our molecular modeling of the two. This is another one that we're very frustrated we don't have crystals of, and it's partly because the reaction makes 8 isomers between optical isomers and positional isomers. But if we look at it, it does exactly what we want. You can actually stop early and get the singly closed derivative. So this is the starting porphyrin, closing one end, closing both ends. The syn and anti are almost exactly the same, absorbing at about 800 nanometers. They're nicely luminescent. So we've made derivatives with zinc and a bunch of other elements, but the zinc are the most well-behaved, and you can see it gives nice fluorescence. This is the absorption, and you can see the close energy match between absorption and emission. This is clearly a fluorescent transition, about 2 nanoseconds, about 13% efficient. So this is what I was telling you, Joe, that you can actually pump this at 800 nanometers, or you could pump at 750 and monitor at 800. It's a rare case where you can pump and detect in the same part of the near infrared. So it's not limited just to pyrene. The same approach works for naphthalene, works for coronene, works for parylene. It works for every fused polycyclic aromatic we've put in the meso position. Again, quantitative yields, mixture of isomers between syn and anti, but the reaction works quite nicely. So if we take these four and compare them, and this is now the naphthal derivative, the pyrenyl derivative, the parylene derivative, and the coronene derivative. The two that are the most redshifted are the parylene derivative, which is at 900 nanometers in solution, and the pyrene derivative. If we look in thin films, they redshift even further, and so now we're getting right where we want. The pyrene is at about 900 nanometers, parylene at about 960. So we've made solar cells with both of those, and before I show you the data, I would caution you that these are still the mixtures of 8 isomers, which isn't what we want. We've now scaled up and made about 3 grams of the parylene derivative, and we're recrystallizing trying to get pure isomers. But it works. It makes a solar cell. You can see that our pyrene derivative goes out to where the absorption spectrum says it should. We're tailing out to 900. This sort of shows you the comparison to CUPC. The efficiency for the device is only about 1%, and that's because our fill factor is relatively poor, and our exciton diffusion length is relatively poor because of the mixture of isomers. And so sometime when I come back short of 53 years from now, I can show you the data with the pure isomers, and I'm hoping that they'll be more like 5 or 6% rather than the 1% we see here. The one thing that gives us a lot of hope is if we compare these to the models that we've seen before. Here's copper thiocyanin, and this is the energy we measure for the HOMO energy in this porphyrin. The energy difference between the HOMO and the LUMO of the acceptor is much smaller, 600 millivolts smaller for my porphyrin than it is for copper PC. So the model I showed you before, this should mean I get a much lower open circuit voltage for my porphyrin than I do for copper PC, and I absolutely don't. You can see that the open circuit voltage for the two are really pretty much identical. So the good news is it means that the steric bulk that I built into this, just to keep it from being too insoluble, so this has dibutyl phenyl groups are what AR is in these two cases. It gives me enough of a standoff at the C60 that I'm still getting a good open circuit voltage. Now what about the parylene derivative? I'm not going to show you the data for that. The parylene derivative wasn't so great. When we estimate the parylene derivative, that is where its oxidation potential is, C60 is not a good enough acceptor. I need a better acceptor for the parylene derivative. I only get about 0.1%, and most of it is from C60. So this is a problem we run into all the time. And so if you're a synthetic chemist looking for a challenge, find acceptors that are as good as fullerenes, and the world will beat a path to your door. Because we really don't have very many. There's C60 and the whole family of C60, C70 compounds, and nothing else comes close to those at this point in time. And we're sort of stuck. So we design all of our chemistries around one LUMO energy for C60, which we could debate about what that is, but it's only one LUMO energy that we're stuck with. All right, so let me take the last 15 minutes or so and talk about what the title of my talk was. Because so far my exciton management hasn't been managed so well. I mean, I've managed it by pushing exciton energies out into the near infrared, but I want to start controlling where they go and start thinking more accurately about what we're doing with excitons, particularly singlets and triplets, in the same way we did with solar cells, or with LEDs. And so if I compare the tetrabenzoporphyrin to this fused bispyrenyl porphyrin, I get two benefits. One of them is I get a redshift, which I wanted, and I also get a significant increase in line width for both the Sorey band and the Q band, right? As I shift from the tetrabenzo to the bispyrenyl derivative. But the big problem is in both cases, I'm left with an open space. That is, if I'm sticking with a porphyrin, I'm always going to have a dead zone between the Sorey and Q bands, right? There's nothing here. The absorbance is quite low. Even though the absorbance at the peaks of the Q and Sorey are high, the absorbance here is really low. And so the first question that we asked ourselves is, well, how do we fill that, right? If we want to keep using porphyrins, especially if we redshift the porphyrins, it's putting it in an area that we would like to fill. So before I tell you how we're going to fill that one, in fact, I'm not going to tell you how we're going to fill that because I don't know how to fill that one yet. We're going to go back to our friend tetrabenzoporphyrin, which has nice narrow lines, which makes the spectroscopy easy to do. But how would I fill the gap? Well, something like tetrazine fills it beautifully. So we started off thinking that we would use tetrazine. Fortunately, we chose not to use tetrazine because it crystallizes too easily. We use diphenyltetrazine, which is shown here, forms a nice amorphous glass. We don't have to worry about crystallization running away while we're trying to make the device. So the thought was, if we absorb in tetracene, this is the singlet absorption, the fluorescence is right here, overlaps very nicely with the absorption of the porphyrin. It's perfect for Forester energy transfer. So this will make a great sensitizer for the porphyrin, because it'll fill this gap. Any energy we absorb here will transfer into the Q band of the porphyrin. This is where my triplet excited state lies and will be great. Until we read a little bit more about tetracenes and realized that there's something else that tetracenes do that's actually quite interesting. We didn't know whether DPT would do this, but we know tetracene in single crystals very efficiently does singlet fission. And that's because the singlet is twice the energy of the triplet. So it's a very simple process, a very fast process in single crystals of tetracene for the singlet to split and make two triplets. So if you think about it from a simple arithmetic standpoint, the energy here is 2 times the energy there. So for one singlet, I can make 2 triplets. And so singlet fission is a form of multiple exciton generation that's very promising, and people are pursuing it now. And the picture then changes a bit. So instead of my doing energy transfer from diphenyl tetracene to the porphyrin, maybe I do singlet fission and I do energy transfer from the porphyrin to the triplet of DPT. That's actually a much more important process than the first one. And the reason, let me just lay this out here a little bit. Remember that I said that we were screwed and we couldn't do better than about 30%, 25%, 30% because of the fact that everything that I absorb relaxes to the energy gap. Right? And so one solution was to make stack cells, which is very expensive and very painful. Well, singlet fission gives us a different approach, right? Because let's say we have the same thing, and I've broken my spectrum here into a green part and a red part, just for simplicity. But no matter where I absorb, I thermalize from the high energy absorbers down to the bottom. And that's a big problem. Well, singlet fission is a process where I take one singlet excited state, I combine it with a singlet ground state, I show in this equation here. A singlet excited state and a singlet ground state makes 2 triplets. So in relaxing, remember when I thermalized before, each one of these little arrows is giving off multiple phonons, and so I'm just heating the crystal up. When I do this, I don't give off any heat at all. This is energy neutral. 2 triplets equals 1 singlet. I haven't given away any energy at all. There's no thermolysis here at all. So if I could do this in my device, that is to say, if I could collect all of my blue and green excitons, do singlet fission and double them and dump them into this red channel, then what ends up happening is I get no thermalization losses from here at all. I dump those into this channel. This red section still gives me a thermalization loss. But if you look at the numbers, Nozick and Mikkel have actually estimated that you can make a 45% efficient single junction cell using this approach. But the key is you can't give up absorbing these photons. Most of the strategies you're going to see that people talk about for singlet fission now are mostly about the absorbing of the high energy photons and not collecting the rest of the spectrum. If you don't collect the rest of the spectrum, you haven't gained anything. You're exactly where you were before you collected it in the first place. And so we first of all needed strategies for collecting them all, and then we need to start understanding the dynamics of singlets and triplets in these highly absorbing systems. So that's what I mostly want to talk about. And so the key is that, remember that the approach here is that we're going to be hopefully doing singlet fission on this tetracene molecule, although we have no idea whether DPT is going to do it or not, because it's only been demonstrated in crystalline tetracene, and DPT is amorphous. And so the question then is, if we pump this, how efficiently can we transfer energy from my sensitizer to my singlet fission material? Because this is the part that's absorbing, if you like, the red and yellow light, and this is what's absorbing the green and blue light in the sort of picture that I showed you here. So imagine that the porphyrin is my model for absorbing red, and the DPT is my model for absorbing green. And so this is what we want to know about, right? I want to know the rates of all these reactions, which is a relatively painful process, although it's not so painful for me because it's done by my collaborator. But it's still a somewhat laborious task. It's all done by transient absorption spectroscopy. And I'm sorry that Bernard isn't here. He loves transient absorbance. This is what he did as a graduate student, and it reminds him of the times gone by. But let me go in, for those of you that don't do transient absorbance, let me give you a quick primer on how transient absorbance works. Because it's the way that I'm actually going to measure the rates of all these reactions, because I can sit and watch one compound convert into another, or one state convert into another state very accurately. So let's say that I've got, this is PTOEP. So what I'm showing in blue is the linear absorbance spectrum. There's my Sorey band and my Q band. So I bring in a pump pulse, and so at some time t equals 0, I pump it up into its excited state. So I depopulate the ground state. I used to have 3 ground state molecules, now I've only got 1. And so if I take the difference spectrum between the t equals 0 spectrum and the t equals tau spectrum, I wind up generating the transient spectrum. And so note that if I take the difference, I've depopulated the ground state, so I'm going to see a negative peak here where I've bleached the ground state. So anything that you see with a negative one is a bleach. That means I've depopulated the ground state. The excited state is going to have a net positive absorption, so I'm going to see a separate absorption spectrum for this molecule in its excited state. But the bigger signals are almost always the bleaches. That the bleach, because these are very intense transitions, but we see both the bleach transitions as well as the growth transitions. So let's take the simplest one, the tetrabenzoporphyrin compound. So I put this in solution, so it's in an inert matrix. It's in THF or methylene chloride, I can't remember which solvent it was in. And I pump it, so I pump it at, I believe this was pumping into the Q band, but I don't remember. I think it was pumping at 600 nanometers, but it doesn't matter. Within about 1/10 of a picosecond, you can see I've got my bleach. There's my Sorey band and my Q band that are bleached. And I've built in an absorption that wasn't present before. So if I wait 10 picoseconds, it seems to have evolved. If I blow the spectrum up just in that part, you can see that over the time course of 10 picoseconds, this band bleaches and this band grows. I didn't know I could do that. That's pretty good. And so the question then is, from this I can derive the time constant for those processes. The time constant is about 400 femtoseconds. That is the intersystem crossing. So this first peak you saw was the singlet. That's what I made instantaneously. 400 femtoseconds is the time constant for converting into the triplet. So the intersystem crossing rate is about 400 femtoseconds. This is exactly what we expected. This is the same you get for iridium compounds. Any heavy metal will give you a very high intersystem crossing rate. If we wait longer, we go out 600 picoseconds, nothing's going on. That's because there is nothing to go on. This compound has a 50 microsecond lifetime. So once I get into the triplet, I'm there for 50 microseconds. And keep in mind, this is ultra-fast spectroscopy. So for them, a graduate lifetime in terms of scaling is a nanosecond. They can't go beyond a nanosecond. That's when their time constants run out. And their system won't go beyond that. So we're pretty far out. This is 3/4 to as far as they can go. So now what happens if I put this into, oh, and if I go, wait a minute, where am I? Yeah, so now if I pump it in DPT, what happens? So I pump it, and I already know that this intersystem crossing is about 400 femtoseconds. So now, promptly within 10 picoseconds, you can see that I'm getting a big bleach for the Sorey and the Q bands, but unlike before, remember at 600 picoseconds there was no change. In DPT, I lose the whole signal, and that's because in DPT I intersystem cross to the triplet, then this transfers energy to the triplet in DPT. If there's no DPT around, it sits in its triplet excited state forever. If I put DPT around, it transfers a triplet back to DPT. The time constant for that's about 35 picoseconds. I can measure the spectrum by simple subtraction. So I can go back to here, subtract out, even at early times, I can subtract out the triplet spectrum for the metal porphyrin compound. I can correct for that, and sure enough, this is the triplet absorption spectrum for DPT. We're very fortunate that somebody long time ago, in the 80s, measured the triplet spectrum by triplet sensitization. It was not a singlet fission experiment. They simply put it in with the triplet sensitizer. And they measured the extinction coefficient for us, which made life really simple, because now I can take my transient absorption spectrum and calculate an efficiency, because I've got the extinction coefficient for the triplet. The yield is about 85%. So that means if I pump the platinum porphyrin, so that means if I pump the platinum porphyrin, 85% yield ends up in the triplet on DPT. So now what happens if I pump DPT? So if I pump the DPT, this is what DPT looks like in an inert matrix. So there's no DPT in contact with DPT, and it's not in contact with the porphyrin. So you can see after 200 picoseconds, nothing has happened. Now if I go put and pump this in the presence of platinum porphyrin, I get, oh, and I should have pointed this out. Sorry about that. This, the cursor is gone. This peak here is actually excited state absorption. This has a very high S1 to S2 absorption coefficient. So this is actually excited state absorption that dominates the bleach. So we don't see a bleach in this case. But we can watch the decay of the absorption, and you can see the singlet. This is a singlet absorption. The singlet absorption decays. It goes down at the same time the bleach shows up in my Squaraines and Q. So with a time constant of about 4.5 picoseconds, energy transfers from the singlet of DPT to the singlet of the platinum porphyrin. If I now wait, it goes through the same exact process as before. Once I'm in the singlet of the platinum porphyrin, it's a 35 picosecond time constant to get to the triplet on DPT with about the same yield. So we've tracked out this, so we know it takes 4.5 picoseconds to get from DPT to platinum porphyrin, and 35 picoseconds to get back to DPT again. But what if there's no platinum porphyrin around? So this is what I get in chloroform solution. If I put it into a thin film, there's no platinum porphyrin in this film. So I can see my singlet absorption decays. I get growth of a new species here, and this is all happening in pretty short time scales, on the order of a few picoseconds is when I'm getting decay of this peak and growth of another signal. I can pull this out again, and guess what? If I pull this out and correct for the singlet absorption, which I can get from the top curve, it exactly matches the triplet. So DPT is making its own triplet. It's doing singlet fission, and we can measure the rate of this process pretty well. Because again, I can fit this to both a combination of singlets and triplets as time goes out. I can measure the rates, and I get two rates. It's a bi-exponential rate. I get about 0.9 picoseconds and about 105 picoseconds. And so we're having a very prompt one. This is about the rate people expect for singlet fission in crystalline materials. It's sub-picosecond, anywhere from 500 femtoseconds to about a picosecond. The reason we have this bi-exponential character is, remember, this is an amorphous film. So this just it doesn't show up so well here, but the bottom one is tetracene, the top one is DPT. This is in the TEM. This is the best I can do to prove to you that it's amorphous, but we see no order in either the X-ray diffraction patterns or the electron diffraction patterns. But the key is it's an amorphous material, and we don't believe that you can do singlet fission everywhere in the solid, but there are certain points in the solid, defect sites or ordered sites, that you can do it. We have some idea what those sites might be, because we can get crystals, not in our thin film, but I can grow crystals intentionally. This is the crystal structure of DPT. Sorry, this doesn't show up very well either. But it doesn't form a herringbone, it forms infinite stacks, and the stacks alternate spacing of 3.5 angstroms and 4 angstroms. The 3.68 angstrom ones are shown here. It's a slip stack, so they're not cofacial, they're actually slipped relative to each other. The cofacial derivative is much wider, it's about 4 angstroms. And so what we think is happening in the film is that the prompt singlet fission that we see, that is the one that's sub-picosecond, is directly decaying at these dimer sites. And the one that's longer, 105 picoseconds, is the time it takes for the singlet exciton to diffuse and find one of these sites. And that this is probably the site where the singlet fission occurs. We're in the process now of trying to do the same measurements on single crystals, but my collaborators tell me that's a real pain in the neck, and so we'll get there, but it's a bit slow going right now to do the same experiments on single crystals as we're doing in the thin films. But how good is the singlet fission efficiency? Well, we can calculate what we expect at AM 1.5. And so remember, in our laser experiments, the intensity is way higher than it is in the solar part of the spectrum. So if we extrapolate back, so this is looking at the laser fluence, if we extrapolate back to what we expect, solar is right in this region someplace, and so if we estimate what the efficiency is, we're getting about 122% yield of triplets. So this is a singlet fission efficiency of about 61%. So for every singlet that we generate 1.2 triplets. So I'd like it to be 2, but I think it's pretty good that we're doing this in an amorphous film already, and I already know where the losses are. Right, the losses are in this diffusion delay. So if we can play some games to decrease the diffusion delay, we'll do even better than that. So let me just show you my last data slide, and then next to the last data slide. This is just sort of recapping. So we measured these rates. So the singlet transfer is about 4.6 picoseconds, 400 femtoseconds, 35 picoseconds. We've made devices with these, and we get about a 0.77 open circuit voltage, so they actually work. Singlet fission goes at a rate of about 1 plus 105 picoseconds. Remember, this is the bi-exponential one. So if we make a device, and these are the efficiencies, so we made a device, and unfortunately we made the wrong device. And after I realized it, we ran out of the porphyrin, and we're making more of it to make the right device. What we did is we made a device where we doped the porphyrin into DPT in this electron donor layer region. And so I'm showing 3 different thicknesses here as well as plain DPT. This is not, don't worry about the current axis. This is monochromatic. This isn't an AM 1.5 measurement. The important thing is when we pump just the porphyrin, we see a nice linear increase as we increase the thickness of the porphyrin layer. So it means that as we make the layer thicker and thicker, we're getting much better diffusion than we got before. In this thickness range with just the platinum porphyrin, it would have stopped at 15 nanometers. Any increase in thickness would not have benefited me at all. So what this experiment demonstrates is we're getting the energy transfer to DPT, but the big problem is that if you remember the rates that I showed you, we have a bit of a problem, and that is that the porphyrin is in contact with this, and so this 1 picosecond as to those dimer states, we're not doing any singlet fission in that device. The platinum porphyrin is quenching the DPT before the singlet fission occurs. So the trick is we need to go back and remake the device and put the platinum porphyrin in between the ITO and the DPT so that it won't quench singlet fission. We expect to be able then to see both singlet fission and the sensitization of the platinum derivative. And so what I've talked today about is a bunch of material systems, some of which look very promising for making solar cells, where we can push that efficiency by red shifting out into the near infrared. But we're starting to spend a lot of time now in trying to understand the nature of these devices, really pull out the role of singlets and triplets in these in the same way we did in organic LEDs and try to optimize the efficiencies by optimizing the exciton dynamics in these materials. And so we're hoping that with the right sort of mixture of materials and insights into these devices, we may well be able to beat the Shockley quasar limit and get devices that have really quite high efficiencies. Let me thank the guys that did the work. CE and Slava both worked on the Squaraines. Slava was the one who did all of the porphyrin chemistry I showed you with the fused pyrene and parylene derivatives. Matt, I didn't talk about his work. Sean and Eric did all of the transient absorption spectroscopy in Steve Bradforth's lab. Steve, Jeremy, and Guodon were involved in most of the aspects of the work I showed you, and these people paid for it. And again, I want to thank you for the opportunity to come, and I'd be happy to take questions.
Thank you.